Hello and welcome to the Math Video Tutor. This chapter we're going to talk about systems of linear equations. And what do I mean by that? I mean, we've talked about, equations of a line, we've drawn the lines on the board and we've plotted them and we've done all these things and we've determined how to write the equation of a line down when we have certain pieces of information like the slope and the y-intercept and all that stuff. That's really fine and dandy, but in this chapter what we're going to learn how to do is solve systems of equations. And what I mean by a system is two or more lines. And we want to find out the solution to that system. And just kind of a little bit of background, if you think about it, in the big picture here, just to give you a preview of what we're going to be doing here, if you have a coordinate axis, okay, and on that axis I go ahead and draw a line, okay, I may have the equation for this line written down somewhere like this, okay. And this line could represent a lot of things. It could represent the profit, or the cost of some goods that you purchase for your company to sell or something like that, as a function of time or whatever. And then you have some other line that might go up like this, okay? And this other line might represent, the cost it takes to pay employees or something like that. In any case, you may have two lines that represent something. Some physical quantity that you're interested in, okay? And you plot them. And if you notice that there is a point when these two lines, whatever they represent, where they intersect. And that's a very special point. This point is called the solution of the system of equations governed by these two lines. So I can write an equation of a line down for this line, because we've been doing that for the last several lessons, and I can also write another equation that governs this line, and where the two of them are both true at the same time, that's called the solution. So what you're really doing here, we're going to learn a lot of different techniques to find this special solution, okay? What it means is it's the point at which both of those lines coincide, so it's the point at which both of those lines are true. What I mean by true is it's the point where that point satisfies both lines at the same time, and that will become very important later on. There's several techniques that we can use to find this solution, okay? And we're going to go over the first one now. The first technique is kind of the most intuitive, the most obvious, and it's graphing, okay? So solving systems of linear equations by graphing. And the big picture is what we're going to do is we're going to plot these lines. We're going to find out where they intersect, and that's going to be our solution. But before we go there, let's just do a couple of kind of warm-up exercises. Let's say I have two lines, x plus y equals 2, and 2x minus y equals 1. Okay, this is what I call a system of equations. This is what you will refer to as a system. This is an equation and this is an equation. And together they're called a system of equations. I could use our different techniques to plot this line, and I can use different techniques to plot this line. The point where they intersect, where they're both true at the same time, that is called the solution. Before we actually get to doing that though, let's do a warm-up exercise. Let's just check. I'm going to give you the point 1, 1. And I want to see, is this point a solution or the solution to this set of equations here, the system? The way to figure that out is just plug it in. If it is indeed true that this is a solution, then this point will satisfy both equations at the same time. So let's do that. Let's plug in x is equal to 1 up in the first equation, y is equal to 1 over here, equals, with a question mark, 2, because it's equal to 2. Of course it is. 2 equals 2. So this point satisfies this first equation. And we know that one half of the deal is satisfied. Now let's check the other half. It's got to also satisfy the second equation. 2 times x, which is 1, minus y, which is 1, equals question mark 1. Well, let's check it out. 2 times 1 is 2, minus 1 equals question mark 1. 2 minus 1 obviously is 1, equals 1. So check. Now, here I arrived, when I use this first equation, 2 equals 2. In this equation, when I use this one, I arrived at 1 equals 1. It really doesn't matter in the end what you come up with. What matters is the point that you plug in here, it must satisfy this equality. And here it did. Again, we put it in here and it satisfied this equality. Because this point satisfied both equalities at the same time, both equations at the same time, it is a solution. So if we were to plot these two lines, we would find that they would intersect at the point 1, 1. And we're going to do that in a minute, but these are just the warm-up exercises, so we want to just take our time here. Let's say if we had the system 2x plus y equals 4, x plus y equals 1. So this is our system, and you'll often notice these curly braces kind of are used to denote system. And let's take 3, negative 2. And let's plug it in. Let's use the first one first. 2, so coming down here, like this, 2 times x, which is 3, plus y, which is negative 2. I'm going to put a parenthesis around the negative 2, just to keep it separate, equals question mark 4. And I put the question mark here to remind myself that I'm just trying to test out to see if the left and the right-hand sides are actually equal. 2 times 3 is 6. Plus a negative is just negative 2 minus 2 equals question mark 4. 6 minus 2 is 4 equals 4. Now I can remove that question mark because I know that it's true. So this point indeed is a solution to this equation. Now let's try the second one. X, which is 3, plus y, which is negative 2. I'm going to put it in parentheses, equals question mark 1. So then I can just say that's 3 minus 2 equals question mark 1. 1 equals 1. So yes, this point, since it satisfies this equation and also this equation, is a solution. In fact, it's the only solution to this system of equations. And the reason I say it's the only solution is we know that this is some line, and we know that this is some other line. There's only one point where those two lines can intersect. And so there's only one solution to that system of equations. Not all systems are like that, and we'll learn about some of those later on. So let's check out another one. This will be the final example of this type. 2x minus 3y equals negative 7. And 4x minus 5y equals 25. This is the system. And I want to test to see if the point 4, 5 is a solution. So that's the point I want to check. So let's put it into this first equation. 2 times x, x is 4, minus 3 times y, y is 5, equals question mark negative 7. 2 times 4 is 8, minus 3 times 5 is 15, equals question mark negative 7. And so when you think about this, 8 minus 15, to figure out how to do that, really all you need to do is take 15, subtract 8, and what you will get is 7, but since the negative number is actually bigger, it's negative 7, and that is indeed equal to negative 7. Now here I'm kind of glossing over some of this addition and subtraction that we're doing here with negative and positive numbers. If you have any trouble following why this is equal to negative 7, then you need to go and pick up my the DVD prior to this one that covers all of that information in great detail. So let's move on. Let's try to plug this point into this equation and see what we get. 4 times x, which is 4, minus 5 times y, which is 5, equals question mark 25. Well, 4 times 4 is 16, minus 25 equals question mark 25. Well, right away you can see that this is not going to be true. This is negative 9. 16 minus 25 is negative 9, and that does not equal 25. I'll put a big X here. This symbol here means not equal to. You just put a strike through your equal sign to remind yourself of what you're doing here. Again, I've done some subtraction here where I've got a smaller number minus a bigger number, and that ends up being a negative 9. What you found here is that this point is not a solution to the system. Okay, it satisfied the first equation, but it did not satisfy the second one. So I'm not going to plot these equations, in specific, but just to kind of get the point home, so that you understand what this means, is that there's two lines here. Let's say this line is something like this. 4, 5 is somewhere over here. Because it satisfied the first equation, okay, what it means is this point did indeed lie along this line, because it was a solution of this line. So that means it had to be on the line for it to even pass the first test. The second line, let's say, goes something like that. I'm just making this up, okay? Because this point did not satisfy the second equation, what it means is this point did not lie on this line, okay? And because it lied on the first line but not on the second line, it's kind of like how we have it drawn here, it's not a solution of that second line, and so by definition it cannot be a solution of this system. Yeah, it's a point on the first line, that's just fine, but it didn't satisfy the second line, and because of that, it is not what we call the solution to this problem, which is solving the system of equations. What we're trying to do here is we're trying to find the common point. We're trying to find the common point that's common to both of these things. And by the way, in nature and science and in all branches of math, you will find that there's example after example after example of things that this type of material is useful for. You will find that there's a trend in something. It could be the population growth of a city, and that might be some line. And then you also might find out the tax revenue or something of those people. And you'll find out that there's always, when they're governed by lines, unless the lines are parallel, there's always going to be an intersection, and there's always going to be some common point that's a solution to whatever it is you're looking at. And many times that point is a sweet spot, and many times that's the optimal spot that you're trying to operate in. If it's like the profit of your company or anything like that, in many cases that point, the intersection of those lines, is in many cases the sweet spot that you want to shoot for, because it satisfies both constraints of whatever it is you're trying to look at. So let's move on into a few other examples and actually show you what I mean when I say that we're going to solve this system, the system of equations, by graphing. What if we had x plus y equals 2 and x minus y equals 0? This is a system of equations. We want to solve it. Okay, well, in this particular chapter in the course, we're going to solve the system of equations by graphing. That means we're going to actually graph these things to figure out the answer. You'll see that there's many ways to solve these things. Now, what we need to do is plot this line and see where they intersect. You can use any method you want to plot the lines. You can make a table of x and y for each line, and you can plot it that way. But in this case, it's much easier just to use the intercept method. Working with this equation right here, okay, and I'm actually going to begin to use a different color marker here, which I think will be useful. If I want to go ahead and say, here's 1, 2, 3, 1, 2, 3. Let's do it that way, okay? If I want to use the intercept method, if x is equal to 0, then y is equal to 2. Because think about it, put 0 here, y has got to be equal to 2. So if x is 0, y is going to be equal to 2. Here's one point right there. If y is equal to 0, take that away, x has got to be equal to 2, because there's nothing here. So if y is 0, x is going to be equal to 2. Okay, so now I've got my first line, which is this one. Okay, now let's work on the second one. If x is equal to 0, then I'm going to have minus y equals 0, and I can just divide out by negative 1, and I'm still going to have y is equal to 0. So 0, 0. Okay, which means the point's going to go right there at the origin. Okay? That's what x is equal to 0. If y is equal to 0, again, I'm going to have x equal to 0. So really, I'm just going to get the same point in either case, which is going to be right there. It doesn't really help me much. So in order to continue to figure out how to plot this guy, what I'm going to do is going to be very simple. I'm just going to move y over here. I'm going to add y to both sides. So what I'm going to have is x equals y. And all I did was move the y over here. Okay? And I can just rearrange that. Y is equal to x. The y-intercept, the intercept method didn't help me too much in this case. So what I'm going to do is I know I have a point at 0, and I've rewritten this equation to y is equal to x. The slope is equal to 1, because the slope is right in front of the x there. It's 1. So I just rise 1, run over to 1, and this is going to be my line right there. Okay? If this equation were different, I could have used the intercept method to plot it, but I just decided to do it this way because of what we had just talked about there. So you can see I've got my two lines, and they intersect right here. They intersect at the point 1, 1, which is the answer to the problem. So that is the solution to the system of equations. So that is what you would circle on your paper is the answer. And I want to stress that you guys can plot the lines on the graph paper that you have in any way that you feel comfortable, really. It's fair game. Everything's fair game. So let's say we have another system. X plus y is equal to 2. X minus y is equal to 4. Now I want to draw my axes like this. Okay, I'm going to say 1, 2, 3, 4, 5. I'm just going to draw some tick marks. 1, 2, 3, 4, 5, 6. Some tick marks like that. And I'm also going to draw some tick marks underneath. I always need those. And I'm going to draw some over to the left just to be consistent. Now let's work with this first equation here. I'm going to switch markers so that we can get good colors here. I'm going to use the intercept method. If x is equal to 0, y is equal to 2. 0, 2. Remember, take x out, y is equal to 2. If I put 0 in for y, 0, x is equal to 2. So, if x, then this goes over here. Because if y is equal to 0, which means on the line here, x is equal to 2, so I'm there. So, I draw my line like this. Okay? Halfway home. Let's work with this one now. If x is equal to 0, y is going to be equal to negative 4. Because if I put a 0 here, I'm going to have negative y equals 4. I'm just going to divide both sides by negative 1. Y equals 4. 0, comma, negative 1, negative 2, negative 3, negative 4. Like that. Okay? Now if I put 0 for y, x is going to be equal to 4. So 0 for y, x is 1, 2, 3, 4. Which is like that. Okay? So what I'm going to have is a line that goes, and I'm going to do my best to draw it fairly straight, which isn't going to be perfect, like this. Now you can kind of convince yourself that the intersection's there. The intersection's at 1, 2, 3, comma, negative 1, which is the answer. Really all you need to do is plot the lines, and you're going to arrive at some intersection point. You just read it right off the graph, and there you go. That's the solution to that system of equations. Okay, we'll move on into one that's just a little bit more complicated. Not too much more complicated, but a little bit more challenging. Let's say we have 3x plus 2y equals negative 8, and 2x minus 3y equals negative 1. This is the system of equations that I would like to plot, that I would like to solve. Okay? So I'm going to have, again, my tick marks. 1, 2, 3, 4, 5, 6, 7. Just kind of get some evenly spaced tick marks all up and down. And you notice I haven't been writing all the numbers because by now you know this is positive and this is negative. this is x, and this is y. Okay? So, what's the best way to do this one? I could do the intercept method. You know, that would be fine. But I just decided to not do it this way and to go ahead and just for some variety show you a different way to plot the equations that we've already seen. If I'm going to solve this for y, I'm going to have 2y equals, move 3x over. I'm going to subtract 3x from both sides. I'm going to have negative 3x minus 8. Okay? All I did was subtract 3x from both sides. You can see all I did was move it over here. Then I'm going to solve for y. I'm going to divide by 2, so that's negative 3 over 2x minus 8 divided by 2 is 4. All I did was divide by 2 on both sides. So now that I have this equation written in this form, after I've rearranged it, what I'm going to do is plot it. My y-intercept is negative 4, which a different color marker will be useful. Negative 1, 2, 3, 4 down here. My slope is negative 3 over 2, which is rise over run. So I just need to make sure and rise downward because it's negative. So negative 1, 2, 3, and then over 2 times to the right, which is over here. So that if I do this right, my line is going to look something like this. Okay? So I'm halfway home. All I need to do is figure out the rest of it. Next thing I'm going to do is solve this equation. I'm going to move the 2x over here by subtracting it. So I'm going to have negative 3y equals negative 2x minus 1. All I did was move the 2x over by subtracting it. I left my negative 3y here, moved this negative, subtract it, so it's going to become a negative 2x minus 1. And then solve for y by dividing by 3. So that's going to be 2/3 x plus 1/3. All I did was divide each term by 3, and of course, since this negative divided by negative, that gives me a positive. Negative divided by negative gives me a positive. Now I want to plot that. My y-intercept is 1/3, which is down here. Okay. My slope is 2 over 3, which means a rise of 2. Here's 1, here's 2, and a run of 3, which is 1, 2, 3. Here's my point here. And then, if I do a good job, I will end up with something like this. Okay? And you always run into a little bit of a inaccuracy here, but basically this point lines up over here with negative 2, comma, negative 1. Okay? So that's the solution there, and that's the intersection point there. And of course, you run into some inaccuracies by freehanding it here on the board without any graph paper. If you use graph paper to do this, and if you use a ruler to draw everything in a straight line, you will arrive at some very good plots. You will arrive at some very good plots, and they will look much cleaner than the ones I'm drawing here on the board, and they will also be very accurate. It's a very accurate way to solve these kinds of problems. Now let's look at a different kind of problem, and this is a really interesting problem. 4x minus 2y equals 8, and also y equals 2x minus 4. And I want to go ahead and plot these two things. Okay. Well, what I'm going to do is I'm going to rearrange this equation. I'm going to solve for y here. Negative 2y equals, I'm going to move my 4x over, so I'm going to have a negative 4x since I'm subtracting it from both sides, plus 8. I'm going to solve for y by dividing by negative 2. I'm going to divide by negative 2, so negative 4 divided by negative 2 just gives me a positive 2x, and then 8 divided by negative 2 gives me a negative 4. Well, looky here. This equation on the bottom is the exact same equation as the one on the top. So if we were to draw that, okay, if we were to draw that, it's going to be the same exact line, okay? But just to be clear about it, the y-intercept is negative 1, 2, 3, 4, so I put a dot here. My slope is 2, so I'm going to rise up 2, 1, 2, over 1, like this, and then I'm going to draw a line like this. That would be how I would draw that one, and then this one would also be the same way I would draw the second one. So what the heck use does this mean? This means that since the two equations are really the same line, there's an infinite number of solutions. I mean, I can pick any point I want on this line, anything, any point on this line. If it satisfies this line, it's definitely going to satisfy the other one because they're actually the same line. And that's going to be thrown in to confuse you every now and then on test. And if you ever find out that the two equations are actually the same, then you don't really have a single number that you're going to be able to write down and say, well, this point is the only solution, because there's an infinity of points that are solutions. Let's do a final example. Let's say we have negative 3/4 x plus y equals 3. And then let's say we have 1/4 x plus y equals negative 1. And I'm going to solve this system here. So I draw my graph. And for me, the easiest way I like to do it is go ahead and, just like we've been doing before, just kind of solve this equation for y. So I'll have, for this one, I'll have y equals, move this term over to the right, so I'm going to add it to both sides. I'll have 3/4 x plus 3. Just add it to both sides. Okay? And if I put my tick marks here for x, well, then my y-intercept is 1, 2, 3, because this is my y-intercept there. And then I can use my slope, rise of 3, 1, 2, 3, run of 1, 2, 3, and 4. So that's right here. Okay? And so I can just use that guy to draw a nice line like this. Next, I'm going to work with this equation, solve for y. Y equals negative 1/4 x minus 1. All I did was move this term to the right. I subtracted 1/4 x from both sides. So I got a negative 1/4 x over here and got the minus 1. Okay, so I can draw more tick marks. I'm going to need those. My y-intercept is negative 1 for this line, which is right there. And I've got a negative slope, so I'm going to rise of negative 1, which is down, and a run of 1, 2, 3, 4, which is like this. Okay? And then if you're real careful, kind of draw some tick marks over here. I think my tick marks are a little bit wide here. I'll draw some tick marks here. Okay. Then what I'm going to do is I'm going to draw this line like that, and it's going to come over here pretty darn close to this point right there, which is negative 4, 0. Okay, and that's the solution. And again, my tick marks aren't exactly perfect, but if you're using graph paper, you'll be able to get those spaced out nicely, and the point is the same. That's basically how you solve systems of equations, by graphing.